Hello everyone. So today onwards, we are going to see the important questions that are related to power system protection. Basically, this power system protection is a basically itself it is a huge, you can say itself it is a huge chapter, and all of the questions that cannot be covered in a particular videos and all. So what I will do, I will pick up the important questions that are related to power system protections. As of now, I have mentioned here only 7 questions, and slowly I will add up the questions and I will bring the videos on that. So first I will explain starting the questions, and maybe I can explain a few other questions in other videos. Subsequently, I will add the questions. Okay. So the first questions give me some example of overvoltage in power systems. Basically, in power systems, if you see, mainly we deals with the you can say short circuit analysis and all from the fault analysis point of view, and we have a sufficient sample space. What are the reasons to calculate the short circuit currents and all, and also like we are aware of much like there are many faults that occurred in a power system and that lead to overcurrent in the transmission lines and power systems, you can say. But we somewhere like I feel like we don't get much information related to overvoltage in power systems. So I'll discuss that point here. Because overvoltage is also kind of a fault. Not only short circuit is a fault, any abnormal condition that occurred in a system that can be termed as a fault. Okay, so I will discuss about what are the reasons of the over voltage fault, you can say. There are many reasons. So let me start with that. Uh, First of all, uh, let's say first I can start with the synchronous generator itself. What is the reason? Like in case of synchronous generator, let's say I have a synchronous generator and it has a synchronous reactance, and you have this load. Okay, and this is your load, and for timing I am considering it is a inductive load, and let me consider a worst case scenario. It is a purely inductive load. Okay, it is a purely inductive load, and we will see what will happen, and this is jxs. Okay, so I hope you know, like at lagging load condition, my synchronous generator operate at overexcited condition. Okay, that means to maintain sufficient voltage at this terminal, your field excitation must be very high, because during lagging load condition, the armature reactions, the nature of the armature reaction will be, you can say, purely demagnetizing. Like if you can recall, uh, let's say this is your field mmf and this is your ef. Okay, so in case of purely lagging load, the armature currents lags the ef, ia, and in this direction I will be having fa, armature mmf that is getting created by the armature current. So your net field next excitation will reduce to here, like okay, if resultant. Okay, and what will happen, that will lead to reduction in the field excitation voltage, effective EMF will also reduce. So to have a sufficient voltage at the terminal, you need to increase your field excitation, and that will increase the resultant EMF. Okay, now for example, your system or synchronous generator was operating at purely lagging load conditions. In that case, your machine is operating at overexcited condition, you can say. Now if you suddenly disconnect this particular load, if you suddenly disconnect the inductive load, then what will happen? Basically, then your armature current will simply become zero, then your ia will simply become zero, and then your the mmf that was getting created by the armature current, that will also become zero. But you have increased your field excitation, and so high, like this field excitation that you have increased to compensate the, you can say, the armature reaction. So what will happen, because of the highly increased field excitation, your terminal voltage will be tremendously high. and that voltage can destroy like the insulation of the insulation of the synchronous generator. And just now I have taken example of an isolated case, but think about the power system network. It is a interconnected system, so each bus and all will be impacted with that high voltage. Okay, so if you suddenly disconnect the inductive loads and all, then there will be rise in the voltage, that we need to take care. Okay, so this is the one of the reason of over voltage. Okay, now what is another reason? Another reason is something we call Ferranti effect. Okay, Ferranti effect comes into picture uh, when there is a long transmission line, and for example your line is lightly loaded. Say, let's say you have this generator, okay, and this is long transmission line, and the load that is connected here, the load terminal, either it is lightly load or maybe sometimes you can consider also it is a no load condition. So in that condition, what will happen? As you know, the long transmission lines and the medium transmission lines and all, we consider the line charging capacitor. Okay, so at light loaded condition or even unloaded condition, the charging current of this line capacitor will be very high, and because of that your receiving end voltage will increase from the sending end voltage. Okay, so your receiving end voltage will become very high if the load, this receiving end is lightly loaded or even unloaded, then the receiving end voltage will be so high. So that is one more reason of the over voltage. So how to like deal with this kind of things? Like we can have a shunt reactor at the receiving end to limit the terminal voltage or the receiving end voltage. Okay, so this is how we have to deal with the over voltage because of the Ferranti effect. Now another thing can happen is like there is one phenomena, we call it as arcing ground phenomena. So now we can see the arcing ground phenomena. So we'll discuss like what is the reason for this arcing ground phenomena, and what will happen if there is arcing ground. So we will discuss all about these things. Okay. So let's say I have a synchronous generator with me. Okay. This is my synchronous generator, and this is the three phases, and armature windings are connected in Easter fashion, you can say, and the neutral of the generator is not grounded. And let's say this is your A phase, B phase, and C phase, right? And this is the A phase, B phase, C phase. And these voltages are basically balanced. So this voltage is E at an angle 0, and this is a B phase voltage. So it will be E at an angle of minus 120 degree, and it will be E at an angle of 120 degree. Okay. Now, in the long transmission lines and all, because there is a potential difference in between conductor and the ground, it will form a capacitor. Okay, so these three lines will have a capacitor with like it is not a physical capacitor, but because of the property of the capacitor kind of a capacitance behavior you will observe in the lines. So these are the, you can say, the fictitious capacitors. Okay, and the value of these capacitors are same. CCC. This is the line capacitance, you can say. And let's say you got a fault at phase A. Okay, so fault, and it is a purely like it is a pure short circuit. So the voltage across this fault, it is 0 volt. So current flowing through this particular capacitor will be 0 ampere. So if fault occurred in a particular phase A or phase B or phase C, the capacitor, the line capacitance behavior, it is in, you can neglect it because no current is flowing through the capacitor. So I can just simply omit it, and we will observe what will happen to the other phases and all. Okay. Now maybe I can do one thing. I can club this to capacitor. Let's say I have this capacitor C, and I am showing like this way. I can show it here. I can show it like this way. Now, basically, one can think like, okay, the fault has occurred here, and there is no return path because neutral is not grounded, and there is no return path, so fault current will not be, the fault current will not flow. Like that, one can think. But what will happen? This fault current will try to close its paths from the through this capacitors. Okay, and a fault current will flow. So first of all, we need to understand what is the effect that is happening on the other healthy phases because of the fault has occurred in one particular phase. It is a LG fault, And if you calculate the voltage at this B and C terminals, let's say phase B voltage, if you write a KVL, you will get 0 minus E at an angle 0 plus E at an angle of minus 120 degree. It is nothing but VV. And if you calculate the VV voltage, you will get root 3 E at an angle of minus 150 degree. So one thing is clear, like the phase voltage has increased by root 3 times. So voltage become the line voltage. So healthy phase voltage, here the B and C are the healthy phases because fault has occurred only in F phase. So these are the healthy phase voltage. And in healthy phases, the voltage magnitude has increased by root 3 times. Now, if you calculate the voltage at phase C, you write a KVL, E at an angle 0 plus E at an angle of 120 degree is equals to VC. You will get VC is equals to root 3E at an angle of plus 150 degree. You can calculate it, you will get this voltage. So phase voltage become line voltage now. Now you can think about the practical scenarios. You'll be having the insulators connected in the lines, so like suspension type insulators and all will be connected like. So this insulator breakdown voltage are decided by the peak voltage of the phase voltage. But here the voltage has increased. Now these voltage may can damage the insulators. Okay, so this is the disadvantage for us. Okay, now we will see what is happening here. Basically, if you write the uh, current equation, let's say my fault current, this is IF, and this is returning from this, and this is the current. So this is, let's say, my IB current, and this is my IC current. So this is how the fault current will flow. So this is the C phase current, let's say, that is flowing through the capacitor. Yeah. So now I want to calculate what is the current. So if you calculate the IB current is nothing but 0 minus VV by minus J by omega C. Okay. So you will get VV omega C by J. So IB is equals to VV is nothing but root 3 E omega C, root 3 E omega C, root 3 E omega C minus 150 minus 1 minus 90. So it is becoming the angle, if you calculate, minus 150 minus 90, so it is become minus 240. So it is 360. So angle is becoming 120 degree. And if you calculate the phase current, this current, it will get 0 minus VC by minus J by omega C. So you will get root 3 E omega C at an angle of uh, 150 minus 90. You will get 60 degree. Okay. So this is the thing that you will get. Now I want to calculate the total fault current. Okay. So fault current IF is equals to IB plus IC. We got root 3 E omega C at an angle of 120 plus root 3 E omega C at an angle of 60 degree. Okay. So if you calculate this particular equation, 1 at an angle of 120 plus 1 at an angle of 60 degree. So you will get up with 3 E omega C at an angle of 90 degree. Now you are getting this particular fault current. Now let's say you have one phase. Just I'm taking one example for the comparison, and you have this capacitor here. Let's say this is Allen capacitors, and this voltage is E at an angle 0, and this particular capacitor value is also C. So capacitive reactance will be nothing but minus J by omega C. If you see the current flowing through the particular capacitor, so IC will be simply E omega C at an angle of what, 90 degree, right? So this will be the capacitor current. So E omega C is the current, you can say, because of per phase. But here you are getting the fault current, which is 3 times of this per phase current. Okay. And if anyhow this particular current magnitude is reached up to 4 to 5 ampere, then this huge amount of current is enough to ionize the faulty path. For example, you got some kind of fault here at any moment, and the moment you got the fault here, the fault current will start flow. But after some time, let's say you removed this faulty path, but since there was a current, let's say this current was around 4 to 5 ampere, so this current, what will do, this current basically ionize this particular path. So even though you have removed the faulty object, still, because of this ionization of the path, you will still see, you can say, arc. The arc will still be visible. So even though you have removed the fault and all, still the arc will come and go like that. So that happens because of this ionization. And since this arc will like come and go, and this particular scenario will create arcing ground phenomena. And it is happening because of, you can say, this line capacitor and the capacitor current. And basically, this fault current is summation of this IB and IC current, which is basically nothing but a summation of the capacitor current. So it is happening because of this capacitor current. So if we want to limit this particular phenomena, or if we want to remove this arcing ground phenomena entirely, first of all, we need to neutralize this particular current. Then only we should be able to neutralize, or we should be able to avoid the arcing ground phenomena. That we will be discussing in the next video. Thank you. If you have any doubt, you can ask me in the chat box. Thank you.